introduction. You already saw him. He talked to you. But anyway, Hugo got his PhD under Israel Goldberg and Rin Kashuk. Then he joined the faculty at the College of William and Mary in 1990, if I'm not mistaken, the same year as...
1989.
Yes, 1989, but you spent 1 year as a postdoc with Bill Helton. Mm-hmm. And then from 1990 till sometime in the 21st century, he was there. And I enjoyed very much these years with Hugo as a colleague and co-author. And now he is at Drexel University. He had written more than 100 research publications, several books, including textbook in linear algebra. He is an author of several very nice results. My favorite, besides our joint papers, of course, is the convexity of the higher rank numerical range. And he is very generous co-author. He always does much more than his fair share. And today he will talk about his new results. So without further ado, I give you Hugo Woerdeman.
Okay, thank you very much, Ilya, for this very nice introduction. We lost my slides, so I hope somebody can pull them back up. I want to start out by thanking very much the organizing committee for inviting me to give this presentation. Please let me know, is the sound okay? Can everybody hear me? Yeah. Okay, thanks, Andre. So I will talk about joint work with my former student, Kenneth de la Rosa, and also joint work with Edward Poon and Ilya Spitkovsky. I want to acknowledge support from the National Science Foundation, and also I want to acknowledge support from the International Linear Algebra Society, because this is a Hans Schneider ILS lecture. And just a few words about Hans Schneider. I have benefited greatly from his leadership. He passed away in 2014. Here he is with his wife about 6 months before he passed away. And if you read his so-called last words, which he wrote himself because he knew that he had a fatal disease, he tells about how he went through tenure at the University of Wisconsin. This was in the early 60s, and he didn't know it at the time, but he heard later that a famous algebraist who was visiting the University of Wisconsin at the time, this algebraist has told the committee, the tenure committee, that every mathematician needs to know linear algebra, but it's not a field of research. And so despite that commentary, he still got his tenure. But when he later heard this story, it really had a profound impact on him. And in 1972, he took over as editor-in-chief of Linear Algebra and its Applications, which at the time was a struggling journal. But under his leadership, we now all know the journal as a vibrant journal that many of us have published in and continue to publish in. And in addition, in 1987, he started with others the so-called International Matrix Group, which in a few years after that became the International Linear Algebra Society, which is a very active society with its own series of conferences, its own journal, and so forth. And also, ILS supports lectures at other conferences. So, I'm very grateful for his leadership and making linear algebra really a recognized field of research. Okay, so let's go to the math. There are two main questions that I want to look at. If you get lost in this first question at some point, you can still pick things up at the second question. So the two main questions I want to look at are the following. The first one is joint work with my former student, Kenneth de la Rosa, and it asks the following question. I start with a normal matrix. It has eigenvalues lambda 1 through lambda n, and I compress this matrix on a k-dimensional subspace. So one way to do that is to choose an orthonormal basis and put put them in a matrix V, which is an isometry, and look at V star AV. And that matrix will have eigenvalues, W1 through WK, and what we're interested in is how those are positioned with respect to the lambdas that we start with. What can we say about that? This is, for instance, of interest in numerical linear algebra, where if you start with a huge matrix and you do a Krylov subspace method, you want to approximate the eigenvalues of the big matrix with eigenvalues of compressions and see how good an approximation those are. And there are many results in that vein, but what we were really looking at is sort of the geometry if you plot these points in the complex plane. And as we'll see, it's even a challenge when we're just talking about 2x2 compressions. So I'll be focusing on that. And in going forward, those two eigenvalues will be Z and W. So that's the first main question. The other main question I want to look at, and this is joint work with Edward Poon and Ilya Spitkovsky, and that's the question, what do matrices look like that have a disk as a numerical range? And then once we've answered that question, we also look at the question, what do matrices look like that have a rank K, higher rank K numerical range as a disk? So those are the two questions. Let's establish some notation and some terminology. So our matrix will be n by n. If we look at the size K compression, another way to think about it is you take a unitary, take U star AU, and you take a K by K principal submatrix of that. That's a size K compression of A. And the eigenvalues of that compression, they're also called Ritz values of the matrix. And a K Ritz set is the set of eigenvalues of such a compression. Okay, all these Ritz values, they lie in the numerical range, which is defined over here. And the numerical range, those are all the complex numbers that you get by taking a unit vector in Cn and compute the inner product Ax with X. And the numerical range has some well-known properties. They include that If you shift the matrix by lambda times the identity, it will also shift the numerical range. And if you multiply the matrix by a number r, then it also multiplies the numerical range by that same number. So we will make use of that because we'll shift things around and rescale it if we so desire. An important property of the numerical range is that it's a convex subset of the complex plane. That's the Toeplitz-Hausdorff theorem, which is about a century old. And it's a bounded set. Everything in the numerical range is of modulus less than the norm of A, the operator norm of A. And since we're talking about finite matrices, the numerical range is also closed. Okay. And another way to think about the numerical range is that it's exactly all the complex numbers that form a one Ritz set of A. So if you take a 1-by-1 compression and look at that value there, that's exactly everything that's in the numerical range. Okay. On the next slide, we're going to define the rank K numerical range, denoted by lambda K of A, and it's a generalization of the numerical range. When K is 1, we just get the classical numerical range. So let's look at that. The rank K numerical range was introduced by Choi, Giesinger, Holbrook, and Cribbs, and they were interested in error-correcting codes in quantum information. And how is it defined? A complex number is in the rank K numerical range if and only if, so Z is in the rank K numerical range, if and only if Z times the K by K identity is a compression of A. So that's the definition, and of course when K equals 1, we're back to the classical numerical range. Now these four authors, they suspected strongly that this rank K numerical range is convex, and they reduced that question to a certain type of matrix equation. And when I saw that, I knew how to do the last step of their proof. So that led to this paper in 2008, where I showed that the rank K numerical range is convex. Soon after that, Chi-Kwong Lee and Raymond Zhe gave another characterization of the rank K numerical range in terms of an intersection of half-planes. So if you look at this line here, each of these inequalities gives you a half-plane of the complex plane, and for each value of t that rotates around, and it describes the rank K numerical range as an intersection of a continuum of half spaces. And so that gives an alternative proof that the rank K numerical range is convex. In this picture, we see what happens when the matrix is normal. So let's say it's a 6 by 6 matrix, and the eigenvalues Z1, Z2, Z3, Z4, Z5, and Z6 are there. Then the classical numerical range is just a convex hull. And how do you get the rank 2 numerical range? What you do is you remove one of the eigenvalues, for instance Z1, and take the convex hull of the others. And you do that for all possibilities of throwing away one of the eigenvalues. And then you take the intersection of that, and that will give you the rank 2 numerical range, which in this picture is this dark gray area. And if you want the rank 3 numerical range, you throw away 2 eigenvalues, take the convex hull of the others, and you take the intersection of doing that. That works for a normal matrix. When the matrix is not normal, it's more complicated than that. But we'll be concerned with the normal matrices. Okay, so those are the main definitions and terminology. So let's move to our first question. So we're given an n by n normal matrix. The eigenvalues are lambda 1 through lambda n. And we're going to pick some value z in the numerical range. And what we're going to ask is, which w's can we pair with z so that z and w together form a 2 Ritz set? That's the question we're going to look at. And what we'll get to is we'll describe the convex hull of that set of w's. That will be our main result in this part. Okay, so what needs to happen? We can always, this 2 by 2 compression, we can always put it in upper triangular form, and so then the eigenvalues z and w are on the diagonal, and there is a 0 below it, and it needs to satisfy this equation. We can assume that the matrix A is diagonal, so what we're looking for are 2 unit vectors, u1 and u2, that are orthogonal to one another, so that this equation is satisfied. And so what you see is that z will be written as a convex combination of the lambdas, where the coefficient in that equation are the modulus squares of the entries of the vector u1. And once you have the vector u1, then the u2, of course, it has to be orthogonal to u1, but it also has to be orthogonal to lambda times u1 because of this 0 here. Okay? And when u1 is not an eigenvector of lambda, then this u2 lies in a subspace of codimension 2. Okay? Any questions so far? So this is the problem we want to look at. Okay, and it really started with this picture. So there is this paper by Carden and Hansen, who were indeed studying the Krylov subspace method, and they had this picture in their paper, but there was no proof of what the picture was showing. So in this case, there is this 4 by 4 matrix, just a diagonal matrix. Here are the eigenvalues, lambda 1, lambda 2, lambda 3, and lambda 4. And there is this point z in the numerical range. And what the picture shows are all possible w's that you can pair with z so that you get a 2 Ritz set. And so I asked my student to see if he could prove that this set of w's is inside the convex hull of those 4 points. And I'll explain what W1 to 3 and W1 to 4 are on the next slide. But in the paper itself, there was no indication of any proof. So so what are these W, 1, 2, 3, and 1, 2, 4, and so forth? Well, that comes from looking at the 3 by 3 case. And we learned the 3 by 3 case from the Carden and Hansen paper, but it goes back at least to the 1950s to this paper. So in the 3 by 3 case, the question is the answer is known. You have this 3 by 3 diagonal matrix. You pick a z in the numerical range. And if z is one of the eigenvalues, let's say if z is lambda 1, then the w's you compared with is this whole line segment lambda 2 to lambda 3. Because in this case, if we think back of the vectors u1 and u2, the vector u1 is just the vector 1, 0, 0, right? That's how you write lambda 1 as a convex combination of lambda 1, lambda 2, and lambda 3. And then the vector u2 just has to be orthogonal to that. So it can be 0, x, y, and that will give you a convex combination of lambda 2 and lambda 3. If z is on the boundary somewhere not at a corner, let's say z is on the line segment between lambda 1 and lambda 2, then the only possible w is the lambda 3. And in this case, of course, the vector u1, which describes z as a convex combination of lambda 1 and lambda 2, is not going to be an eigenvector of the matrix lambda. And so you get a reduction of two, from 3 dimensions, you go down to 1 dimension. And so there's only a unique w in this case. And if z is in the interior, then there's also a unique w, and we're going to call that w1, 2, 3, y1, 2, 3, because the corners are lambda 1, lambda 2, and lambda 3. So later on, we'll have triangles with other corners, lambda 1, lambda 2, and lambda 4, for instance, and then we'll call it w1, 2, 4. Okay. So in this case, the only point you compare z with is this w1, 2, 3, and it's the so-called isogonal conjugate of z. And how does that work geometrically? What you do is from lambda 1, you draw a line through z, and you reflect that line around the bisector of lambda 1. And that will give you this line, this orange line going down like this. You do the same from lambda 2. You draw a line lambda 2 to z. You reflect it through the bisector in lambda 2, and then you get this line. And again, you do the same from lambda 3 on. And it's a theorem, it's Seva's theorem, that those 3 lines, those 3 orange lines, they all go through the same point. And that's the isogonal conjugate. Okay. Questions? No? Okay. So here's the general picture. The main case we're interested in is when z is in the numerical range, but it's not in the rank 2 numerical range, nor it's in the boundary. Those latter cases are actually much easier. So the hard case is this case. So here we have a 5 by 5 matrix. Our result is only about the case when the lambdas are on the boundary of the numerical range. I'll make a remark about that later. So we have a picture like this. So lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. This point z, it lies in the triangle lambda 1, lambda 2, lambda 3, for instance. And so a W we compare it with is W1, 2, 3. That's one option. And another values that we compared with are lambda 4 and lambda 5. Because if we write Z as a convex combination of lambda 1, lambda 2, lambda 3, then the vector U1 only has non-zeros in the first three components. And I can take, for instance, 0, 0, 0, 1 as a vector orthogonal to it, and that will give me lambda 4. And similar, lambda 5, I can pair Z with. So viewing Z as a convex combination of lambda 1, lambda 2, and lambda 3, I can see that these 3 points are possible values for my W. Okay? I can pair Z with one of these 3 values, and they form a 2 Ritz set. Similarly, I can view Z as being in the triangle with corners lambda 1, lambda 2, and lambda 4. So that means I can pair it with W1, 2, 4. It also means I can pair it with lambda 3, and I can pair it with lambda 5. And finally, Z belongs to this triangle, lambda 1, lambda 2, lambda 5. And so I can pair Z with W1, 2, 5, with lambda 3 and lambda 4. So that's how I get this list here at the bottom. And then the statement is that any possible W that I can pair Z with to form a 2 Ritz set must lie in this convex hull of this set of points. So that's the so here's the full statement. I'm going to take a normal matrix. We're going to assume that the eigenvalues do not lie on the same line. What happens if they are on the same line? Then we're basically in the Hermitian case, and then we can just use Cauchy interlacing to describe all possible 2 Ritz sets. So that's already covered there. So we assume that they're not all on the same line. And our restriction is that no eigenvalue is in the interior of the numerical range. And then we pick a value in the numerical range, and we look at all the W's that form a 2 Ritz set. Z and W form a 2 Ritz set, and the convex hull of those values is equal to this set R of A of Z. Okay. And I showed you on the previous slide how this construction works. If Z is in the numerical range, but not in the rank 2 numerical range, nor on the boundary, I view Z as a member of one of these triangles, and I associate with that triangle a W and the other eigenvalues. And I do that for each possible triangle, and I take the convex hull of those points. So that's, I didn't explain the notation here, but it's what I showed you on the previous slide. If the Z is in the rank 2 numerical range, then the convex hull of all the possible W's is the whole numerical range. And why is that? Because if Z is in the rank 2 numerical range, I can throw out any of the eigenvalues and write Z as a convex combination of the others. And that means I can pair Z with any of the eigenvalues. And the last case is when Z is on the boundary, let's say in this segment lambda A, lambda B, then I just take the convex hull of the other eigenvalues. I throw out lambda A and lambda B, and I take the convex hull of the remaining ones. Now, there's a little bit more written here because you have to take care of the case when there's higher multiplicity and so forth. But that's why it looks a little bit more modeled than what I just said, but that's the essential idea. And the last two cases are actually easy to prove. The first case is what's hard to prove. And I want to say a few words about that. So if we go back to this picture, what we need to do is we need to draw a line from lambda 3 to W123 and show that all the possible W's that I can pair Z with are on the right-hand side of that line. And the same when I draw a line from 123 to 125, and also the same when I draw a line from W125 to lambda 5. Okay, and I'm just going to take a sip of water. Sorry about that. I want to show you a little bit of the flavor of the proof because it's very technical and it's quite long. And one of the things I hope is that maybe one of you have a more shorter and more conceptual proof. So that would be great. So maybe I'll stand on this side for a little bit. So what do we need to do? We need to, for instance, show, oops, how do I go back? I can only go forward. Sorry. Oops. How do I go back? Oh, the small button, okay. There are only 3 buttons on this thing, so I should have guessed that. Okay, there we go. So we need to show, for instance, this situation. And what we do is we shift the matrix and we rotate it around, and that line then becomes the imaginary axis. And then we need to prove this, that whenever I pair Z with W, the real part of W has to be non-negative. So that's one case. And then in this case, when we have a line between 2 of these isogonal conjugates, we also make a reduction like that. Okay. And part of the proof is to figure out which isogonal conjugates. Because if you go back to this picture, we're not showing that things are on the right-hand side of this line between what W123 and W124. So you also have to, so it gets very, anyway, and then ultimately we reduce it to showing that a matrix like this is positive semi-definite. And this matrix, and then we use induction to do that. So it's very technical, it goes on for pages and pages, and really I was surprised at how much work it was to prove this result. Maybe I shouldn't say too much about what else is written here, but hopefully you get a flavor of the technicality of the proof. So it seems like there should be a more conceptual proof. Okay, so we did prove, we did provide the convex hull for the 2 Ritz sets. If we fix a Z, the convex hull of the possible W's we can pair with. Oh, and there's one other point I wanted to make. Actually, the surprising part of it for me is not so much the blue region, but it's the yellow region. So you have a 5x5 matrix. You compress it to a 2x2 matrix. And one of the eigenvalues is here, And then immediately all this yellow part is forbidden for what you pair it with. So there's some repelling going on between the eigenvalues of a compression. Okay, so what didn't we cover? We don't know what happens when we look at 3 Ritz sets or 4 Ritz sets. The set of W's always seems to be star-shaped. We were not able to prove that, so that's another open question. And the last open question is, what happens when one of the eigenvalues is in the interior? Then there seems to be, then the result doesn't go through, because, for instance, in this example, we have lambda 1, lambda 2, lambda 3, and then lambda 4 in the middle. Here are the 2 isogonal conjugates. And the blue region, which is the set of W's, is not contained in the convex hull of W123, W124, and lambda 3 and lambda 4. So that's...
Do you know if that blue region for this example is convex?
If it's convex, in general, it won't be convex.
Yes, I was just wondering if there's any, if it is in this case, and if there's some reason for that.
Oh, I don't know, but in general, it's not convex. As I said, we do expect it to be star-shaped. This one, I agree, it looks convex, but we haven't tested that on a... So, I mean, when you move lambda 4 to the boundary, it's not going to be convex anymore, so, or it might not be convex anymore, so we don't know exactly what happened. So those are open questions. Okay, so then I want to, and I guess another indication why this is in general a hard question is that if we understand these Ritz sets very well, we will also be able to solve Sendov's conjecture completely. So what does Sendov's conjecture say? It says that if you have a polynomial with all its roots inside the circle, in the unit circle, and you take the roots of the derivative, that within distance 1, there's always a root of the derivative within distance 1 of every root of the polynomial. So if you take a root of the polynomial p, within distance 1, there must be a root of the derivative of that polynomial. That's the Sendov's conjecture, which was stated back in 1959. It's known for size up to 8, and it's known for other special cases. And very recently, Terry Tao proved that Sendov's conjecture is true from some big N on, although we don't know what that big N is, but there's a gap there. And you can phrase it as a problem on Ritz values, because if you take the normal matrix with eigenvalues lambda 1 through lambda n, then the roots of the derivative show up as an n-1 Ritz set. And the way to do it is to choose a unitary where one of the columns has all the magnitudes the same. So for instance, the last column can be 1, 1, 1, 1 divided by square root n. If you compute the nth entry of this matrix, it's going to be 1 over n p prime over p. And of course, we know from Kramer's rule that an entry of the inverse is the quotient of 2 determinants. So the p prime shows up as this determinant of this n by n n minus 1 by n minus 1 compression. So if we know Ritz sets well, one can easily also solve Sandow's conjecture. By the way, in this particular case, you have some extra information, namely that the average of the lambdas is the same as the average of the w's. Okay. So that's my first part, and I think I'm going to make it in time. So the next part is joint work with Edward Poon and Ilya Spitkovsky. I should have put their names on this slides, but it will show up on soon. But this theorem is also joined with them. So what we were interested in is I have a matrix and I know its numerical range is a disk. What kind of matrices have that property? And by shifting and by rescaling the numerical range, we may as well assume that the numerical range is the closed unit disk. Okay, and what's the statement? A matrix has numerical range equal to the closed unit disk if and only if I can write it in this form. I can write B as 2 times P star Q, where the column block matrix PQ is an isometry, or in other words, P star P plus Q star Q is the identity, and P and Q are rectangular of size n minus 1 by n. And so that's an if and only if statement. Whenever I choose P and Q in that form and write down this B, I get a numerical range that is the unit disk and vice versa. And here's an indication of the proof. If P and Q exists, then we can write down this equality here, and that shows that this expression is always positive semi-definite, and that tells you then that the numerical range is inside the disk. And due to P and Q being of size n minus 1 by n, this expression is always singular, so that tells you that e to the it is in the numerical range, and then those two statements together tells you that the numerical range is the full disk. And the other direction is similar. It's a busy slide. We won't go through the whole thing. But again, you have the numerical ranges in the unit disk. That tells you that this is a positive semi-definite matrix for any t. So you have a trigonometric polynomial that's non-negative on the circle. That means there's a Fayet-Ries factorization of it. And then you have to argue that because this expression is singular for any t, you can actually choose P and Q to be of size n minus 1 times n. And we won't go through that argument, but it's here. Okay, so that's characterized as matrices whose numerical range is the unit disk. Then we were wondering what happens with the rank K numerical range. When is that a disk? And again, we can always make the center 0. So we're going to ask which matrices have the rank K numerical range equal to a disk with center 0 and with radius r. Okay, what needs to happen in that case is that this trigonometric polynomial of degree 1, r times the identity minus the real part of z times b, which I can also write out in this form, that must always be singular for any point on the circle. And actually, the 0 eigenvalue must be the kth lowest eigenvalue. So this is a Hermitian matrix. 0 is one of its eigenvalues, and it must be the kth lowest eigenvalue if the rank k numerical range is going to be this circle. So we need to study trigonometric polynomials with that property, and so this trigonometric polynomial has degree 1. We're going to study it when the trigonometric polynomial has degree m. So it has this form. It takes on Hermitian values on the circles. That means that Qj is Q minus J star. And what we want to do is factor Q of z as Pz star J times Pz, where P is a matrix polynomial of degree m, and J is a signature matrix that has k minus 1 negative eigenvalues. It has 0 as an eigenvalue, and then it has n minus k positive eigenvalues. So it's, well, technically it's not a signature matrix. There's 0 in there, but aside from the 0, it's plus or minus 1. And so J is singular. If J were non-singular, then there's a whole literature on this kind of factorizations, and because it has applications in Wiener-Hopf equations and in systems and control and filter design, so there are many reasons to study this factorization, but almost all the literature is on the non-singular case, and so to get what we want, we needed a new result there. Okay, so that's joint work with Edward Poon and Ilya Spitkovsky. And here's our results. So we have our trigonometric polynomial. We're going to assume that there are 2 and m plus 1 different points on the circle where this trigonometric polynomial is singular. Remember, we want the trigonometric polynomial to be singular everywhere, but it's enough to assume it for 2 and m plus 1 different points. In addition, we're going to assume that at nm of these points, the kernel is one-dimensional, so they're spanned by these vectors xj. And then with xj and these nodes e to the t j, we built this kind of van der Monde type matrix, and the assumption is that van der Monde type matrix is invertible. These are 2 and 3 are generic conditions. For instance, if Q is of size 1 by 1 when n is 1, then these xj's are just the number 1, and then this is truly a van der Monde matrix with different nodes, which we know to be invertible. Okay, under these conditions, we have this factorization. So we can find a matrix polynomial P of z, and we can find a signature matrix J, which has k minus 1 negative eigenvalues and n minus k positive eigenvalues, and this equation holds. And the 0, we threw it out, and we also threw out one of the rows of the P. So the P matrix, the matrix polynomials of size n minus 1 by n, okay? Which, of course, if J has a 0 in it, you can do it in that way. Okay, so if we have 2 and m plus 1 points where Q is singular and we have these additional conditions, we can always find this factorization. And the proof is very constructive, actually. You have these bases of these kernels, you put them in a matrix. You have these nodes, you put them in a diagonal matrix. This is our Van der Monde type matrix, which is invertible. We built this matrix out of the coefficients of Q and the V and the D. And then we're going to take minus my inverse. And a main part of the proof is showing that this X we find is Hermitian. And actually surprising to me is that it's easy to show that property for the off-diagonal entries, but to show that the diagonal entries are actually real, that takes more work, but it can be done. And then you build this matrix gamma X, which is X here with the coefficients of Q bordered here, and then you subtract this matrix, the shifted X, and so what you notice is that, for instance, if you add the diagonal entries of gamma X, you get Q0. And if you add the next diagonal, you get Q1 and so forth. Okay, so a big part of the proof is to show that gamma X is Hermitian, and also that it has this low rank. And if you have a low rank Hermitian matrix, you can factor it in this form. This J is a signature matrix sitting in the middle. And so it's some matrix P times J, or P star times J times P. And the size is determined by the rank. So the J is n minus 1 by n minus 1. And then these coefficients here, that give you the coefficients of the polynomial. So it's a very constructive proof. Okay, so we were interested in in when is the rank K numerical radius a disk? And the answer is under some additional conditions, these generic conditions, it's exactly when B can be written as in this form, 2p0 jp1, where J is a signature matrix with k minus 1 negative ones and n minus k plus ones, and this equality should also be satisfied. So that's our characterization. Of course, when k is 1, then the J is just the identity, and then we have our previous result. Okay. Some additional remarks. There is this theorem by Anderson, which states that if you have an n by n matrix whose numerical range is inside the closed unit disk, and if it contains n plus 1 points on the disk, then the numerical range must be the whole disk. So we sort of get a generalization of this result, if you look at it in the right way, I guess. So that the fact that the numerical range is inside the closed disk, that gives you that this trigonometric polynomial is positive semi-definite. And that tells you actually that these roots on the circle are actually double roots. So there are, in fact, 2n plus 2 conditions on the matrix. And you can reduce that to 2n plus 1. And we have an analog for the rank K numerical radius. So you need 2n plus 1 roots on R times the unit circle. And then you have these additional dimension 1 kernel conditions. Let me mention also a couple of open problems. There's the Gao-Wang and Wu conjecture from 2016. What it says that if A is a partial isometry on an n-dimensional space and the numerical range is a disk, then the disk must necessarily be centered at the origin. That's the conjecture. These three authors proved that that was true up to size 4. Then Ilya with co-authors Suleiman and Weigert, they proved it also works for n equals 5. And Ilya Spitkovsky and Elias Weigert, they also proved this statement when the rank of A is n minus 1. And my understanding is that there may be some update on this later in this week. No? No, okay. But who knows, maybe one of you. Okay, so Ilya indicates that I should stop talking, so let me just give you the list of the papers that I talked about, and thank you very much.
Okay, thank you very much, Hugo, for this very interesting talk. Any questions? Question from Michael? Here is the mic, Mike.
Yeah, so what, I mean, this sort of looks like some of the things that appear when you do proofs of like the Fayet-Ries theorem.
Yeah, but whenever you want to do these Fayet-Ries factorization, so Michael asked about the matrix X in that expression gamma X. It's kind of a standard trick when you want to factorize a trigonometric polynomial. You're basically taking an X and border it with the coefficients of Q, and then you subtract the shifted versions of X.
So is this some sort of a Schur complement then? Can you interpret it that way?
So we haven't looked at that. In this case, the things are indefinite, right? So, but maybe you can find X as a Schur complement of some infinite tuplets matrix. That could very well be. But now you're dealing with something indefinite, so it may be harder than the positive definite case that we looked at, right?
Okay, thanks.
Other questions?
Yes, hello. Could you show us again your picture concerning higher order numerical range with 2 polygons, hexagons, I believe? It was like 4th or 5th.
Right. I know now how to go back.
Yes.
That helps.
Oh, not this one, yes. So, as far as I understand, this construction works for normal matrices. So now the question is, do you have any constructive recipe how to find higher order numerical range for the general case of not normal matrices?
Right, so what you do is this, it's this inequality here. So you pick an angle, T, and then you look at this matrix. It's some Hermitian matrix. You look at the kth eigenvalue of it, and then the Z should be in that half space defined by this equation. And you do this for all angles.
Mm-hmm.
So for each angle, you get some half space, and you do this for all angles.
So then you will not get polygon, but in general, also higher order numerical range could be smooth curve, yes?
Right. So for instance, it could be a disk, as we showed at the end.
Okay, thank you very much.
And people have written programs to
Also
draw
question.
that if you, right.
Okay.
Panos?
Can you tell us a comment about the non-normality of these matrices? How close to normal or how far
Oh,
away
they're
from?
very far from normal.
Yeah,
They're like nilpotent matrices that.
like Jordan blocks, for example.
Right,
Thank you.
exactly.
Okay, one more question from here.
Thank you for talk. I would like ask, you have some interesting commutation relation in some theorem, like fermionic anti-commutation relation. In Samuel theorem, I don't remember which one, this was anti-commutation relation.
Further down.
No, father, maybe. Yet more. Oh, yeah, this was before. Yeah, just this here in that theorem. And you have just in theorem 2, P star P plus Q star Q. So this is classical anti-commutation relation for Fermi fields, Fermi particles. My question is, because how you found this? You come from physical approach or just by chance, by calculation?
No, I guess, I mean, a lot of the things about the numerical range you can say using this trigonometric polynomial. And then if it's positive semi-definite, then you can factorize it in this form. So the way I look at it is factorization of trigonometric polynomials.
So this is just calculation.
Right.
But you have another theorem, I don't, when you have with matrix J, such an anti-commutation relation, here, that should be some physics, yes. Maybe Professor Rzeczkowski knows something about this, because this is like a generation of fermionic business. Did you also?
I didn't do myself, but yeah, I mean, these numerical ranges are also studied in particles.
So anyway, I thank you, and I like your talk very much.
Okay,
Thank you very much.
Thank you. Nikhil?
More questions? Yeah.
So in this part of the talk, you were studying eigenvalues of compressions by arbitrary subspaces. Are there some nice characterizations of compressions by Krylov subspaces? By specific, I mean, those are not all subspaces, right? Not all subspaces are Krylov subspaces. So is there a notion of higher rank numerical range restricted to only subspaces generated by cyclic vectors that has some nice property?
Not that. I think that will be a new invention that may be very interesting to look at. I'm not aware of such notion in the literature, right? But it could be very interesting to look at. Thank you. Nick?
Yes, in the case of the classical numerical range, there's this very nice parametrization by Ando of all operators whose numerical range is contained in the disk.
Right.
I'm wondering if there's something similar for the higher rank numerical ranges.
So I mean, one way to look at Ando's result is the statement that the numerical range is inside the disk if and only if this trigonometric polynomial is positive semi-definite. And so in the rank K numerical range, it becomes that this trigonometric polynomial has fixed signature. And if you want the K numerical range to be exactly a circle, it has to be, then the Kth eigenvalue always has to be 0. So I think in that way you can sort of view sort of a generalization of Ando's result to this case.
So you could actually get a parameterization.
For matrices with Ray. So So we have this statement here. It's not exactly if and only if, because we do have these conditions that are generically true. So you may have to make an additional assumption on your matrix so that this trigonometric polynomial is actually only rank 1 deficient in certain directions. So there's a little bit of subtlety there, but.
Thank you.
Yeah, can see the question in the back.
Hello, yeah, it's me. Regarding the star-shapedness conjecture of the two Ritz sets you showed in the first half, is there a contender already for the star centers? Like, if it is star-shaped, the center has to be something, I don't know, the average of the corners or something, or is that also open what the star center could be potentially? Because for example, for the C numerical range in the 80s, it was known that for some special cases, it's star-shaped and the star center is something, and that something also generalized to arbitrary matrices. So that's kind of where my question comes from.
So I guess we really studied the general case where these eigenvalues are on the boundary of the numerical range, and then we always noticed that the star-shaped feature. We didn't do enough experimenting with eigenvalues inside, so I'm not sure what happens in that case. But it could very well be that it's always star-shaped. I don't know if that answers your question, but...
I mean, kind of, my question was whether there, from some special cases, it's clear that if it's star-shaped, then the star center has to be of some specific known form. Or,
yeah, we did have a conjecture of what you could use as the center.
Right, okay.
It escapes me right now. Yeah. And these corners will be these orthogonal conjugates and some of the eigenvalues, right?
Yeah, I see. Thank you.
Right.
Are there any more questions? Well, probably that's enough. It was sufficient feedback as it was, and we're imposing on available lunchtime. So let us thank the speaker again. Okay, who should I give it back to?